Dr. William H. Joyce is the chairman and CEO of Advanced Fusion Systems, the retired former chairman of the board and chief executive officer of Nalco Company, leading provider of integrated water treatment and process improvement services, chemicals, and equipment programs for industrial and institutional applications. He served in those roles from 2003 to 2007. From 2001 to 2003, he was chairman and chief executive officer of Hercules Incorporated, a global manufacturer of chemical specialties. Prior to that, chairman, president, CEO of Union Carbide from 96 through 2001. In 99, presided over the sale of Union Carbide to Dow Chemical, served as vice chair of Dow Chemical until his departure. So right now, we're very honored to have Dr. William Joyce begin his presentation, which will give us an overview of what we can do practically about these problems, and then afterwards I'll introduce George Anderson, and we'll go from there. Thank you. Dr. Joyce.
Thanks, Chuck. I appreciate all the work that you and others have done to put this on, and thank all of you for being here. AFS is a new company using new technology, previously tested in military applications, and we offer protective devices and sources for EMP and GIC and EMP test services. Here's a problem that we all have, getting people to listen to advice about terrible things that may not happen for years. The tsunami stones are 127 feet above sea level. So now it comes time to build a nuclear plant just below these stones. And the first thing they do is dig out the ground to get closer to sea level. So I think that's a problem that faces all of us, but it's a challenge we're going to have to find a way to overcome. I want to talk a little bit about EMP and non-nuclear EMP. I want to go one slide back. The best available technology that we have now is MOVs and lightning gas. Depending on these devices is questionable in a nuclear EMP environment and unacceptable in a non-nuclear EMP environment. And the following graph sets some current technologies and AFS technology against the threats in a scaled view. The dark line there is an EMP pulse from a nuclear explosion. The light red is a non-nuclear, and of course lightning is shown there. This is a log-log scale, so what seems like a close comparison between two is really an order of magnitude more dangerous. So the top of that graph has a lot of threats to it. The blue line shows where MIL 188 devices would give protection, and the green line there is an AFS Spytron protection. Let's talk a little bit more about non-nuclear EMP. Numerous powerful non-nuclear sources have been demonstrated. Some have been certified by the U.S. government having field strength in excess of 250 kV per meter. Some of these devices, including the big ones, are portable. This presents a threat that exceeds the protection that you would get from MIL 188. These threats are relatively inexpensive to make and lend themselves to multiple simultaneous attacks at different locations. I've shown here, I'm hoping to show here.
You went one too fast. Go back.
There it is. This is a 35 kV per meter system that was built in collaboration with the U.S. Army. And I might add the more modern and more powerful ones fit in the same kind of van. So they're really relatively easy to build one of those and drive by your favorite substation and take it back to the 18th century. Mill 188 is the current government standard for high altitude EMP protection. It was good at the time, but it needs updating. The utilization of a swept narrowband source for shield effectiveness ignores the physics of the response of materials to an ultra-wide EMP pulse. The slow response of Mill 188 designs allow too much energy leakage before the protective device becomes capable. AFS offers some testing services that exceed Mill 188 and gives us a realistic test environment for nuclear and non-nuclear environments. I just mentioned, yeah, I know it's black. I just mentioned our devices depend on a new version of electron tubes. A few words on how they differ from semiconductive devices. We use tubes that were originally developed for military EMP simulation and high-power microwave applications. They're designed for repeated operation in this extreme transient environment, so they're very robust. Solid-state devices can fail by piezoelectric-induced overstress, leading to single-arc failure, thermally induced overload, and cascade failure. The AFS tubes are significantly faster than the fastest power semiconductive devices. And the tubes are not subject to DVDT or DIDT constraints as semiconductors. Typical slew rates are well in excess of megavolts per microsecond. For DC operation, we use a pulsatron. It's a high vacuum cold cathode triode tube. I won't go through all the specifications there, but you see, despite its small size of 5-inch diameter and 12 inches long, it can handle 500 kV and 250,000 amps. The Bitron is what we need for AC systems. It's a bidirectional electron tube designed for AC power electronic switching and control operations. Voltage ranges to 1.2 million volts and hundreds of thousands of amps. For overvoltage protection, including EMP protection in excess of Mill 188, the Bitron's designed to operate in EMP environment. It's capable of handling repeated pulses at a multi-kilohertz rep rate. Size varies with voltage, as you would expect. Units below 35 kV are less than 16 inches in diameter and no more than 36 inches long. Units for 1.2 million volts are approximately 6 feet in diameter, and their length is basically the same as you see insulating chains for high voltage applications. All systems provide external control signals to trip external protective systems. All systems are self-resetting and are capable of withstanding and protecting multiple events in rapid succession. These devices also protect against lightning or any other voltage surge that your system might encounter. Here's a Bitron that's being built for a utility. The charge here is for 30 kV and 10,000 amps continuous duty, up to 1,000 degrees Fahrenheit without cooling. It's 36 inches long, 18 inches in diameter, but it weighs almost 800 pounds. Oh, sorry. Nope. This is a Bitron for 125 kV and 5 Ka. It's 7 feet long and 2 feet in diameter. Now for testing, This is a major move because we're talking about devices for which we haven't had test equipment to handle the kind of things that they're designed for. So as part of our commitment to this area, we're constructing world-class EMP test facilities. I think most of you know that when they run electrical tests, the common idea is to test the high voltage at a very low amperage and then test the high amperage at a very low voltage. Or you'll run a swept narrow beam rather than an ultra-wide EMP pulse. Particularly for something new like our technology, but really for anything coming along. It's essential that devices meet realistic conditions under full voltage and full amperage and subjected to fields that may be there in real life. EMP test facilities of on-load testing devices at up to 250 kV per meter and up to 1 million volts are what we're doing, and we're not aware of anything else where that type of tests are available. This facility can inject simulated GIC fault signals with a user-definable waveform that accurately simulates real-world GIC waveforms up to 25 kV DC and 100 Ka. That means we can say what we think the pulse design looks like, but if you want to try something different, we can match whatever where you're interested. Whether that's for GIC faults, or we can do the same for EMP. We'll be able to test devices at line voltages to 1.2 million volts AC or DC under load conditions of 10 megawatts and in sub 100 picosecond rise time pulsed electric field environment of greater than 250 kV per meter. And again, with a user definable waveform that accurately simulates the real world conditions. While the facility is primarily for AFS production and research work, we'll make it available to other users, including competitors, because this is something that we all need to work together and get over the hurdle. And while we think we have a good idea, maybe somebody has a better one. The facility also can successfully create SG-EMP pulses as well. It covers the full channel. All right, I give up. There you go. This is our test cell number 1. You can see a person standing in the background next to the high voltage transformer to give you an idea of scale. These are 80 feet long, 40 feet wide, and 20 feet high with a door of 16 by 16, so we can get most things into this chamber. In addition to the one we just talked about, we're building 2 more that are 135 feet by 50 feet by 50 feet. All cells will create arbitrary EMP waveforms and test at 250 kV per meter. All cells can duplicate magnetic field conditions of the largest transmission lines. They'll have digital instrumentation, greater than 25 gigasamples per second per channel on 12 simultaneous channels, and less than 17 picosecond resolution. Just in case you're curious, here's what a 10 hertz, 15 kilojoule, 250 kV per meter pulse modulator looks like. In normal working, it drops into the tank below it. You can see it pictured here on the right, already in the tank. This is an artist's concept of a transformer protected from both EMP and GIC with an EPS system. Each device senses the pulse coming down the line and connects to ground through a low impedance connection. The device implements field collapse protocol. Detection and operation are autonomous. The device provides hardened data output containing information on the system status and an EMP event alert. And it's available from about 4,000 volts to 1.2 million volts. There are bulkhead-mounted devices that give transient suppression and EMP protection for shielded rooms. AFS also has some interest in protecting from solar storms. Whoop. One more. Yeah, field collapse is our approach for both EMP and GIC. For neutral blocking, for Kappaman method GIC neutral blocking, we have a switch for that as well. It's available as an integrated system through Phoenix Electric, or it's available to anybody that would have a need for that kind of a device. It looks like this. This is 35 kV, 100 KA, 24 inches long and 18 inches in diameter. Just a word about what we're protecting against. If you're going to have a nuclear event, the fundamental physics governing the generation of the EMP pulse demands that if an E3 pulse is there, both an E1 and E2 will also be present. A reverse is not necessarily true. One can generate a non-nuclear EMP pulse that only has E1. So caution's advised if you're designing a protective system. There's a little sense in protecting just for E3 in an environment where you're expecting E1. Just a final thought. We're a new company, and we have new products, but we're not a garage operation. This is our building in Newtown, Connecticut, 250,000 square feet. It looks much prettier with the horizontal view, but this shows you the size and the magnitude of the event. So thank you very much for your attention. Appreciate your interest.
Now I'm going to introduce briefly George Anderson, who's going to tell you a word about himself. But you should know that he's employed at Crown Iron Works. The company's been around since 1878. Was not founded by him in 1878, but some relatives he probably eventually got to know. He's been in multiple capacities, director, senior, or executive vice president, where he developed new processes and designs of major equipment, safety engineering, and international sales support. In 2009, he founded Emprimus to work on similar technology that is going to be spoken about in just a moment. George, why don't you say a few words and then introduce Gale? And that mic should be on.
I guess this is working. I'll cut my remarks pretty quick here because we're sort of tight on time all day, I think. But one thing I've learned in about 40 years of being the engineer for safety and chief engineer for design is that good thoughts don't accomplish very much for any purpose, and results really depend on something that is built, tested, and put in service. This often requires a few years to prepare something like that, but real results only respect real functioning safeguards. In 2001, I heard of EMP, and that's now 12 years ago. It's kind of a slow pace that has me a little nervous about the whole thing. Another thing I think is important is the idea that we have to have a little faster pace in the future. I think it's picking up this year. I see a lot of activity I didn't used to see. Actual hardening of some sites, data centers, and that kind of thing being reported around the United States in particular. Gale was quite a find for me. 2007 and 2008, we got together and founded Emprimus, and he's both an experienced electrical engineer. He has experience at XL, used to be NSP in Minnesota, both as an engineer and as a lawyer for the company. He's experienced in high-level risk management and insurance. That was another stint he had. So I hope you'll listen to him carefully as he defines a few things we're trying to figure out about high-priority things to actually have real products, and also some means of remediation of those risks. And as you listen, please keep in mind a couple things. Whatever you do, wherever you are, try to help advance the cause of protecting our infrastructure And lastly, the words of an effective, impatient activist, General George S. Patton. I hope you'll ponder these words. Fill the unforgiving minute with 60 seconds of distance run. I'll leave you with Gale. Thank you.
Thank you very much, Chuck, for inviting us and for all of your patience in being here. And thank each of you for advancing the ball in some way in this whole field to help protect our country. One of the ways that we are trying to advance the ball is with some new products and extensive modeling and testing. So with that, one of the first things we've heard from NERC is that one of the biggest risks to the grid is if there is grid instability caused by a GMD event because of half-cycle saturation on the transformers. And it could be a blackout, but some utilities have said to us, well, a blackout will happen before there's any damage to equipment. So let's take that as item number one. Here are some recent blackouts in the U.S., and you can see that the estimated cost from the U.S. government is in the billions of dollars to the customer. So I think the cost to the customer has been overlooked in each of these situations. Why is the blackout important? For another reason, all of these big power plants, you don't just turn the switch to start them. They have huge feed water pumps, emission control systems, coal handling systems that take an enormous amount of power. So you first have to start a bunch of other generators to even get the large generators going, and then a coal plant, it takes hours and hours for the boiler to heat up to be hot enough to even generate steam. So the 2003 Northeast blackout, obviously pretty real. Here's what NERC said about that, and here's why we believe that procedures will be inadequate as a way to control or to protect the grid. There are many, many variables that will occur, whether it's the strength of the storm, the direction of the storm, what generators are in service, out of service, purchases, sales, on and on, time of day, the load level, etc. And so utilities have said all of their operators need specific simulation training for the conditions, and if the conditions are different, the operators won't know what to do. Well, look what NERC said about the 2003 blackout, and it's essentially the exact same thing that they're going to say about a GMD event. Start from the bottom. Inadequate training, inadequate anticipatory analysis, inadequate communication, inadequate voltage control. It'll be all the same reasons. And guess what will happen? The blackout will last for a long time. Here's a big item. And the utilities have not had the data, perhaps, to focus on this issue until now. Idaho National Labs tested for harmonic issues at the distribution level. The utilities have been focusing on the high voltage level. At the distribution level, you get 33% harmonics at about 100 to 120 amps of current in the neutral. Well, the standard, IEEE standard is 5%, 7.5% for a short period of time. That's going to cause damage to equipment, to motors, to rotors, to condensers, et cetera, et cetera. Louis Marti from Hydro One came out with an IEEE paper that said you're going to have damage to rotors, generator rotors, if you have more than 50 amps of current per phase. We're going to talk about, when we are designing equipment, we look at what the maximum credible threat is in order to come up with a design standard. What is some of the maximum credible threats? Data was filed for the Chester, Maine substation, thanks to what's going on in Maine. So for 20 years, they recorded the GIC, the ground-induced current in the neutral of transformers at that substation. John Kappelman correlated that data with magnetometer data from one of the nearest sources of a magnetometer. When you correlate that and put it together, and just look at the bottom line, because we got to go quickly here. If you look at where there's 100 amps in the neutral, this position down here, you see that's at about 250 nanotesla per minute. So if you ramp that up to 5,000 nanotesla per minute for a 100-year storm, you multiply that by 20. You're going to get 2,000 amps in the neutral. Remember what we were talking about for harmonics at only 100 amps. And remember what Louis Marti just said, you'll have damage to rotors at 50 amps in the neutral. So we're suggesting this is a pretty serious issue. You've seen this before, the coronal mass ejection, the size of it compared to Jupiter, compared to the Earth. What does it do? Look what it does to transformers on the bottom two pictures. The left one was in South Africa, the right one was Salem, New Jersey. And you can see once again the size of some of that. When we've done modeling, we've done extensive modeling with Power World. Power World was originated by Professor Tom Overby from the University of Illinois. So he's been able to simulate and put GIC currents on load flows to simulate what happens when there's a solar event while the grid is in operation. And by the way, John Kappelman has some modeling, Siemens now does, GE now does, Mitsubishi, etc. This didn't exist a year or two ago. So here are two individuals that have done an estimation of what the field will be for a 100-year event. At the top, John Kappelman's numbers are about 15.2 volts per kilometer, and there's 20 volts per kilometer on average for Ani Polkanen from Catholic University, although he's got a range of 10 to 50. So we simulated putting current blocking devices in the grid in Wisconsin, and we have a partnership that we're working with ATC in Wisconsin, so they've given us actual transformer and line data and so forth, and so we did this. And you can see what happens the more blockers you put in. This is only 25. You can see the total GIC. You can see the total GIC going down in the system, and you can see the megavar loss going down. For a while, the utilities didn't have the software tools to say, well, I don't think the grid will even go down. Well, here we are, and you can see here that with no blocking devices, the Wisconsin grid will collapse at about the 100-year level for a solar storm. And then as we start adding blocking devices, you can see the grid becomes more and more resilient. And this is out of a total of 350 transformers, and this is blocking only 27. So what we're saying is by blocking 10%, 15, 20%, you get significant resiliency in the grid, and it's not an overwhelming, huge, costly issue. Here's another really interesting graph. Remember before I said actual data could point to 2,000 amps of current in the neutral. So we simulated with Power World. Over in Wisconsin, we said, what's the effect on the neighboring utilities if we blocked Wisconsin? Because we've heard from many utilities, oh, well, if we block, it'll push it to the neighboring utilities. Or vice versa, it doesn't do us any good to block until all the neighboring utilities do. Well, let's take a look at that. We'll call this a myth buster. So if you look at here, this is before there's any blocking. We took the 6 highest interconnections from the Wisconsin grid to the surrounding states. But look at here how high the current is on some of these. Here, it's almost 3,000 amps. So under a simulation, it is confirming what the actual data could be. And then, of course, there's 2,000, 1,500, 1,000, etc. And when we put blocking in Wisconsin, look what happens. These lines, virtually nothing happens. Now the reason it doesn't go down is we're not putting blocking in the neighboring states. But if you look at that, it completely debunks the myth of we're going to add current to the surrounding states or vice versa. So there's no reason a state shouldn't go ahead immediately and do blocking. They will not adversely impact their neighbors. This was the system that we started out with and is still offered for sale, which is basically here you have the solid ground connection, and during GIC it goes through a resistor and a capacitor bank. That doesn't allow the DC current to go through, but the AC does. That's been tested. It's been simulated at the University of Manitoba. It's been tested at Kima Labs in Philadelphia, and of course Idaho National Lab that was talked about this morning. It was placed into a high voltage grid, and it operated just fine. In fact, here's a kind of a synopsis. These lines over here are with no blocking. So when there's current injection, DC current injection of different levels, you can see that here. That's what the curve would look like. But as soon as blocking was put in, and it was arbitrarily set at different time limits here, it immediately went to zero in every case where it was set and goes across. So it just stops the block, it stops that altogether. Our guys were out at the site, and when they were injecting DC, the transformer would be humming and shaking and noisy, and as soon as the blocking went in, it stopped, just like that. So we've come up with an even beefier system. When we did some testing, we found, in modeling, we found that in the Wisconsin grid, at the 100-year storm level, we checked the voltage level at every single substation, and with one exception, the highest that it was at was 2,000 volts. The first, the first model that we had was capable of operating at 4,000 volts, but there was a one long line, 150 kilometer line. So 150 times 20 volts is 3,000 volts, and so we said, you know, for long lines in other states, maybe even for 30 volts per kilometer, let's make a beefier unit. So we did that with 2 capacitor banks, and it's now 8,000. So it's 8 kV, which will handle, we think, virtually any situation. If there happens to be an extra long line for EMP at 50 volts per kilometer, we can add more capacitor banks and it'll still operate. We also have a thyristor bank, which some utilities were saying, well, what happens if I have multiple faults during a GMD event? Very unlikely, very, very, very unlikely. But we said, okay, we'll deal with it. And so we put in a thyristor bank, so this can fire repeatedly so that a fault will not destroy or take out the capacitors that are put there for protection. So here's the upgraded model, and you can see that it's got 2 capacitor banks here at the top, so the size of it hasn't changed. It's still 8 feet by 8 feet. We just pushed everything and got it closer. We use SEL Electronics Schweitzer. We had electronics made by a California firm that worked just fine, but we said, you know, for the confidence of the utility industry, we're going to use a proven gold standard, if you will, and so we've entered into a further partnership with Schweitzer Electronics and, of course, ABB parts. I'm not going to go into all of this, we don't have time for it, but we're demonstrating to the utilities that there is substantial backup and redundancy with every component and so forth, so they don't ever have to worry about not having an effective ground as defined by the code. As a quick example to that, it's solid ground. The utilities most of the time want to operate in solid ground. But an effective ground under the code is still to operate through a power resistor and capacitor banks. This technology was developed by utilities, quite frankly, in 1983, 30 years ago. But they only had this. They didn't have the advancement of solid-state electronics, which now allows us to keep it in a solid ground 99% of the time and then switch over to this only when it's needed. So we're trying to satisfy the issues that utilities have. We did a study here as to any unintended consequences. If you get a bunch of these installed in the grid, is it somehow going to affect the operation of the grid? The University of Manitoba in short order said, no, no problem. EPRI, the Electric Power Research Institute, has also just studied that and said, no problem. This is Schweitzer installing the unit over in the ATC grid in Wisconsin. The cost for this ranges, if you bought them one at a time, probably as high as $320,000, and the installation is $25 to $50. Utilities now, when there's a solar storm warning, PJM as an example does it on the East Coast, Con Ed, Dominion, they redispatch energy, meaning they back down baseload generation and they start a bunch of peaking units so they have bar generating capability. Instead of having 2 trucks running at their engines at full speed in the parking lot, they want to back the trucks down and have 20 cars starting and running at it. But the problem with that is the cost of the energy is much higher, and that energy is that cost is passed on to you. That cost in 1 to 2 years could pay for remediation of the whole grid. So just to put this in perspective. We also think that when transformers are humming and shaking and all these things are going on, or you get 1,000 amps or 3,000 amps in the neutral, we think that blocking can certainly save the life or extend the life of a transformer. The average age of transformers today is 42 years. So you put that in perspective, we're talking about an old fleet to begin with. There we are.
That's it.
This one.
I'm Bill Harris with the Foundation for Resilient Society. So my question, though, for the panel altogether is first for Bill Joyce. It has to do with the effect of NERC has determined to eliminate a standard for physical security even at critical electric facilities. However, the states have police powers, and we could have standards at the state level. So my question has to do with the intentional RF weapons, such as can be put in a van. Do you think, given the potential for this kind of damage at multiple sites with non-nuclear EMP, that there ought to be action at the state level, given that there's not going to be any action in the near future at the federal level?
Let me just comment on a van with an EMP weapon board. I don't think doing a very good job of protecting your perimeter is going to help you at all. But I might ask Gale with his background. There's a lot of other advantages I know from a chemical plant of having good protection, and Gale can probably comment on the case of a power plant.
And I'm also wondering, to add to his question, is in the same way that the states have police powers, might the states be used to compel utilities at the local level to get the protection from either of companies like yourselves as an enforcement or a provocateur of protection that would create demand for your product?
Let me address this a little bit. In the recent weeks, the utilities have now had to focus on physical security based on the individual or individuals that attempted to shoot at the transformers for Southern California Edison. But different folks in the military have told us that there's an advantage to, and they are now looking at facilities with a multi-layered security approach, meaning you have one layer at the outer boundaries and you change what you're doing for security at different levels as you're getting closer and closer to the heart of the operation. So distance is your friend, and you would want to put at least some kinds of detectors. We also incidentally make those as well. But some kinds of detectors for various threats as far out in the perimeter as you can with a smart type of video system, and then you want to do increasing protection until you finally would do the MIL standard 188.125 and so forth on protection on the electronics themselves. And so it's kind of a mixed answer, if you will. I think we're just learning about a lot of the security. I can ask you guys a question. How many of you in all of your college days had a single course or a single professor ever talk about security and mix it in with what was going on, you know, whether it's a design standard or something else in engineering? I didn't have one. I don't know about you, but so I think the world is changing.
Okay, we have time for one question. That'll be brief as long as the answer is also brief, like it depends or something like that. Here we go. Identify yourself, please.
It depends, won't do. I'm Frank Gaffney with the Center for Security Policy. I just wanted to drill down for a moment on the finding of the University of Manitoba and the industry's own internal research arm, that there isn't, in fact, some sort of bleed-out problem, I don't know the technical term for it, elsewhere in the grid if you protect part of it. That's not the industry's position, as I understand it. Could you explain how its own research arm is apparently at odds?
Well, the studies that I talked about with EPRI and the University of Manitoba have to do with operational issues like, are you going to affect relaying in a location because of the insertion of blockers? But our studies that we just finished with Power World would suggest you're not going to push the energy around on the grid to different systems, providing you put enough blockers in your own system. It changes and settles down the whole level of GIC such that you are not going to adversely affect your neighbors. And so, to our knowledge, this is the first study that's ever been done which concretely shows that.
Thank you. And one of the things we're going to do is many of these studies that can be shared publicly. In some cases, there may be some classified sections, but most of them can be shared. Will be part of our conference proceedings, like the ones from last year. And we'll continue to meet with many of these folks in the course of the coming months and gather ongoing research results and policy questions such as the ones you're raising. So let's give them a quick round of applause. And as we're leaving, I'm going to have Jeff Weiss come to the front. We're not even going to take time for a stretch break. Yes.
In the back, I'm going to leave some brochures or information packets for those that are interested in both the detection and the solid ground.
Thank you for mentioning that, Gale. We have other packets of information in the back tables as well, and if you are from a group that have such, you're welcome to leave them there as well. And we're about ready to begin with our next section. And I think I'll leave this